Alright, in this video, I'm going to cover section 15.2, which is about double integral over general region. And in the previous videos, we covered the double integral over rectangles. So the region of integration for double integral was just a rectangle in the previous two videos. Now in this video, we're gonna generalize it to more general region than just rectangle. So let me start with an example. Let D be the region on xy plane bounded by x is equal to 0, x is equal to 1, y is equal to 0, and y is equal to x squared. What is this? Well, pictorially, it should look like this. So x is equal to 0 is the y-axis, x is equal to 1 is the axis like this, vertical axis, vertical line, and y is equal to 0 is the x-axis, and y is equal to x squared is the parabola, which looks like this. And then the D is the region bounded by those, so that means this portion, this part. This is our D. And this curve is y is equal to x squared, so this curve is. Okay, and then by using the set notation, this is written as this. Remember the set notation? So D is equal to the set of all points xy such that x is between 0 and 1. So this is 0 and 1, 0 and 1. And y is between 0 and x squared. The region described in this way is this region. Okay. And you have to get used to the set notation. So this means the set of all xy such that. Remember this bar means such that. Such that. Sometimes they use a colon. Either way is okay. Such that. And then you just write down the condition. X is between 0 and 1. And y is between 0 and x squared. Okay. Then now, the question is this. Find the volume of the solid that lies below g is equal to x squared plus y squared plus 1, and this region D on the xy plane. So pictorially, what is this? Well, this is, actually we have seen this example before. This is a paraboloid, so to speak, and its z-intercept is 1, so paraboloid floating in the air, like this. X and y, z. Let me just write that. This is z-axis. And it's rotated paraboloid, like this. And now D is the region. D is the region which looks like this on the xy plane. So if you write it down here, it looks like this. Okay. This part, this is our D. This is D. And then the question is asking you to find the volume of the solid between the paraboloid and this parabola on the xy plane. So it looks like this. And then you just go up like this. Oops. And then it's a bit hard to write down the nice picture, but it looks kind of like this. this kind of shape. This part. Okay, this is the solid we're looking for. Like this. Okay, and then essentially the idea is the same as the case of a rectangular region. So last time in the previous videos, we dealt with the case where D is like a rectangle, more like just a rectangle like this. But in this case, it's not rectangle, but the idea is this. Remember when we did double integral over a rectangle? What we did was to basically fix one of the variables first, namely consider one of the variables as a constant, and then view the other variable as a variable, and we just integrate with respect to the variable. Then we basically do the same thing here. Then, for example, in this case, let's fix x first. Fix x, meaning that we consider x as a constant. We view x as a constant, so namely, let's view x as a constant. Okay, and we consider only y as a variable, meaning and vary y. But from what to what? Well, y is between 0 and x squared, so we just vary y from 0 to x squared. So vary y from 0 to x squared. Or in other words, more pictorially, what I'm doing here is this. We just fix x somewhere somewhere between 0 and 1. We fix x. And then we vary the y value, and that would be from 0 to this parabola x squared for each x. So therefore, we get like what? Well, the function we integrate, it's a function that lies above the region. That's the paraboloid here. So this is a function we integrate. So we integrate x squared plus y squared plus 1. With respect to y, our variable is only y at this moment. And then y is from 0 to x squared. And then, look, this is an integral with y. And then once you carry out this integration with y, the variable y disappears. And then what you're left with is some expression containing x. Namely, you get a function of x. And then you vary x after that from what to what? Well, x is only between 0 and 1. Well, here, x is between 0 and 1. So x is from 0 to 1. 0 to 1. This is the integral you have to set up. And then the computation is the same as the case of rectangular region. So if you look at the inner integral, so to speak, and you sort of partially integrate this by considering x as a constant and y as a variable. So here x squared is viewed as just a constant, and if you integrate with y, you get just x squared plus y. And if you integrate y squared with y, you get 1/3 y cubed, plus you integrate 1 with y, you get y. And then you evaluate this for y0 to y x squared. And then you just leave dx here. And then you just plug in here to this y, this y, this y, as usual. And then you get what? X to the power 4 plus 1/3 x to the power 6 plus x squared. And if you plug in 0, you just get 0. So that's it. And then you integrate this with x. And then this is just the integral in calculus 1. And if you work this out, you're supposed to get 61 over 105. So that's a way to compute double integral over a general region. Okay, then now, just like the case of integral over a rectangular region, you can switch the order of integration. Namely, you may fix y first and vary x, and then integrate with x first. That's essentially what's called Fubini's theorem. So here's another solution. fix y first. So consider, that means that's the same as to consider y as a constant. Then, what does that mean? That means pictorially, and for this, better to look at the picture. The region is the same. And then here, 1, 1. And then now you fix y. All right. And then now for each fixed y between actually 0 and 1 in this picture, in order for you to be in this shaded region D, for each y, your x value has to start from here on the parabola to this vertical line. And the corresponding x value here is root y, right? Because this one is y is equal to x squared. And that's the same as, well, actually, on this region, that's the same as x is equal to root y. So for each fixed y, the starting x value is root y, and then all over to x is equal to 1. So that means if you fix y, namely if you consider y as a constant, then the x value varies from root y to 1. So therefore, the integral you have to set up is this. The function you integrate is the same as before, and then you integrate this with x from what to what? Well, from root y to 1. And then, if you carry out this integration with x, the variable x will disappear, and what you'll be left with is only y, and then you integrate with y. And y is, in order for you to be in this shaded region, your y value is between 0 and 1. So it's from 0, 1. Okay. And then let's compute it. This is 0, 1. And then you integrate this with x, you get 1/3 x cubed, plus you integrate this with x, you get y squared x, because you are viewing y as a constant. And you integrate 1 with x, you get x. And then you evaluate this from x is equal to root y to x is equal to 1, and then dy. And then this becomes, if you work this out, you get, it's a little bit complicated than previous case. Plus 1, if you plug in 1, then minus 1/3 y root y plus y cubed root y plus root y and dy. And in principle, you could work this out. And I'm not going to do the details, but you are supposed to get the same answer as before, namely 61 over 105. Okay. So, as this example tells you, in principle, it doesn't matter which variable you fix first, namely which variable you integrate first. But in practice, sometimes one is simpler than the other computationally. Just like the case of a rectangular region. Oops. Okay, so in general, let me just write down the general formula. In general, let D be a region in the xy plane. The volume of the solid between D and some function z is equal to f of xy is given by this double integral double integral of the function dA, and over D we often write this way. So this is a called double integral. This is called the double integral. Over the region D. And here dA is dx dy. Or that's the same as dy dx, depending on which variable you integrate first. And then pictorially, like this. So you suppose you have some surface like this given by z is equal to f of xy. And then you have some region on the xy plane. And if you look at region above like this, and then the volume of this solid here is given by this double integral. And the way to compute is essentially in the way I did. And of course, strictly speaking, if the surface is above the xy plane, like this picture, xy plane, that's a volume. And if the surface is below the xy plane, namely on this side, the surface comes on this side, and then in that case, what you get is a negative number, so it's a negative volume times negative 1. Okay, so that's a double integral over general region, and you have to get used to this. The only way to get used to it is to work out a bunch of examples. Okay, so let's do this one. Evaluate a double integral 4y squared dA, where D is the triangle with a vertices 0, 1, 1, 2, and 4, 1. Okay, how are we going to do this? So first of all, for most of the problems for double integral, I would say it's almost impossible to do the calculation without actually writing down the almost a precise picture for the region you integrate over. So let's write down the picture for the triangle on the xy plane. X, y, and then 1, 0 is here. This is one. I'm sorry, 0, 1 is here. And then it's 1, 2, 4, 1. And 4, 1 is here. And the 1, 2 is somewhere under here. So this is the triangle. So we integrate over this triangular region. Okay. Then now, like I said, in principle, it doesn't matter which variable you fix first and which variable you integrate first. But in practice, it does matter. But anyhow, in this case, let's do this way. Let's first fix our y, and namely we view as a constant. So that means you just pick up y. And then let's ask this question. In order for you to be in this triangle, in the region, namely in this triangle, your x value has to vary from what to what? Well, namely for each y, in order for you to be inside the triangle, you have to be in between those 2 points here. What is this? What is this point? And what is this point? What is the x coordinate of this point? What is the x coordinate of this point? Well, for this, you have to calculate the equation for this line. This is y is equal to x plus 1. And then this line is y is equal to negative 1/3 x plus 7/3. Okay, this is your exercise to understand why this equation is like this. Then now, we want to find the x value. So that means you have to solve this for x. X is y minus 1 in this case. And if you solve this for x, you get x is equal to negative 3y plus 7. So that means your x varies from y minus 1 to negative 3y plus 7. So then your x varies from y minus 1 to okay. Therefore, the given integral, this double integral for y squared d, is written as what? Well, first of all, you integrate for y squared, and then you integrate with x, and x varies from y minus 1 to negative 3y plus 7. And then you integrate with y. Then what's y? Well, y is from the lowest possible point for y is here. That's 1. And the highest possible point. Well, let me just fix this. Okay, the highest possible y value is this top of this mountain. That's 2. So it's 1, 2, 2. Okay, so this is the integral you have to set up. And then once you set up integral like this, everything is mechanical. And then just for a piece of terminology, strictly speaking, this part is called the double integral. And this portion is called the iterated integral. Iterated integral. But let's don't worry too much about the difference. Just a terminology. Anyhow, then this gives you 1, 2, and then you integrate this with x. So you sort of partially integrate with x. And then x is from, let's do this. And then in order to emphasize that the variable you are working with x, it's better to put x is equal to here. And then dy. And then if you plug in, what do you get? You get plus 7 minus 1. And then you integrate with dy. And if you simplify this, simplify the integrand, you are supposed to get cubed plus 32y squared dy. And then if you work this out, so this is just a calculus one. So if you work this out, you get 44/3. So that's the answer. Then now, that's fine, but what if you integrate this in the other way around? Namely, you instead of fixing y, what if you fix x first and you integrate vertically first? Then in that case, you're going to be in trouble actually. The reason is because of the shape of the graph, shape of the region. So here's x and here's y. And in this case, we have triangle like this. And then, well, here's 4. Then now, if you want to fix x first, this is 1. Depending on where you are, you get different y values. Indeed, if you fix your x here between 0 and 1, for this fixed x, your y value varies from 1 to this line, namely x plus 1. On the other hand, if you fix your x between 1 to 4 here, then your y value varies from 1 to line here, that's going to be this. So that means you have to basically separate the integral in 2 different parts. In principle, you could do this, but it's not a good idea. So then which one should you choose? Well, so basically there are 2 different ways of calculating double integral. Either you integrate with x first or y first. And which one should you choose? Well, it depends on the region. Okay, it depends on the given region. So in general, So let me just give you the general scheme. In general, if your region is like this, so you have a curve given by y is equal to some function of x, h of x, and then on the above you have y's function of some function of y's some function of x. Namely, both of them are solved for y. Then in your region is between a and b for x. If this is your d, in this case, better to fix x value first. For each fixed x, your y is from h of x to g of x. So in this case, if you are in this situation, double integral of some function of x and y, dA, this is written as you fix x first, and for each fixed x, your y value changes. In order for you to be in that region, your y has to be h of x from h of x to g of x. And then you integrate with with y, with y. And then once you carry out this integration, the variable y disappears, and the only thing you are left with is x. And then you move around x, move x, in this case from a to b. And then dx. So basically, for this case, fix x and vary y. And then book calls this type 1, but you don't really have to memorize which one is type 1, which one is type 2. But let me just note this type 1. And the other type, namely type 2, is actually, so you have y-axis, and then you have two curves like this, and then right curve is solved for x, so x is equal to h of y. And then the other curve is x is equal to g of y, like this. And then your y value is from some constant to another constant, like this. And then in this case, what you should do is to fix y, and for each fixed y, your x varies from here to here, h of y to g of y. And so in this case, the double integral is written as, so you integrate with x first by fixing y, and then h of y, g of y, g of y. And then if you carry out this integration, this is an integral with x, and you plug in those to x variables. So after you carry out this integration, you'll be left with only y, no x. And then you integrate with a y from a to b. And then, so this is, you fix y and vary x. And then book calls this type 2. But like I said, you don't really have to memorize which one is type 1, which one is type 2. So with this said, let's go back to this example. For this example is, so to speak, type 1. And then, no, I'm sorry, not type 1, sorry. Actually, type 2. Type 2. And indeed, the curve here corresponds to the line here. And this curve corresponds to this line here. And then this horizontal line here, the bottom line, is literally the bottom line here. And then this part here actually collapses to the point. So the top line is just a point here. So basically, for the previous example, it just happens that those 2 points, those two are the same point. That's the previous example. So that's why, for this case, better to integrate with x first by fixing y. And that's what we did here. Okay. And then on the other hand, this example, the fourth example, is what? Well, the fourth example is like this, right? And this example is actually can be viewed as both type 1, type 2, because you may view it as like type 2 by considering this curve here as this line here, and the curve here is like this curve, and then this bottom line here is the x-axis, and then top line corresponds to just a point here. Or you may view it as like this by considering this horizontal line as this curve, and then top curve is this part, right? And then this vertical line is this vertical line, and then the left vertical line is just a point, the origin here. So for this case, you may consider as either type 1 or type 2, whichever you like. So that's why you could compute in both ways. Okay, now let's work out a what time do we have? Let's work out one more example for this video. Yes. Example. Evaluate double integral over the region D, y dA. So the function you integrate is just y, where D is bounded by y is equal to x minus 6 and x is equal to y squared. Bounded by those. So here's the answer. Like I said, I would say it's almost impossible to do a double integral problem without sketching the region. So here, in this case, first, what is this? X is equal to y squared. This is a parabola. So y is equal to x squared is a parabola opening in the direction of y-axis. But if you switch square here, what you get is like this parabola. So this one, y is equal to x squared, is a parabola like this. So this is x is equal to y squared. And then you have y is equal to x minus 6. This is just a line with y-intercept negative 6, slope 1. And then this looks like, maybe we need more space. This looks like this. This line here is y is equal to x minus 6. And then the region D is the region bounded by those. That's this. Okay. And then let's compute the point of intersection. You can compute this as 3 and this as negative 2. Yes. All right. Then now, so this one is actually this, type 2, so to speak. You are sandwiched by two curves. Both of them are like, should be solved for x. Indeed, this curve is here, and the other curve, the curve on the right, is actually the line. And then those two horizontal lines actually collapse to the points here and here in this case. Okay, then, so that means you fix y first and you integrate with x. So you fix y and you integrate with x, and that's gonna be from here to here. So you have to solve this for a x. This is x is equal to y plus 6. And then this is already solved for x. So fix y. Then for each fixed x, fix y, and then for each fixed y, x varies from y squared to y plus 6. Okay, so therefore, the given double integral is written as, well, double integral y, and you integrate with x, that's from y squared to y plus 6, and then you integrate with y, and then y is from here. Those numbers you have to calculate. You have to actually compute the points of intersection. Oh, let me fix this. Okay, I got the picture back. So you have to calculate the points of intersections by equating those two. So by plugging in this y to here and solve the quadratic equation. So this is your exercise. All right, and then, wait a second, this is also erased. dy dA is equal to the integral from -2 to 3. Okay, and then all you have to do is just carry this out, carry out the integral. So like I said, once you set up this iterated integral, so to speak, the computation is more or less mechanical. So you leave the outer integral, and then you integrate this with x, you get like this. And then in order to emphasize the variable you are working on, better to put x is equal to y squared, x is equal to y plus 6, and then dy. And then this is equal to -2, 3, and then y plus 6 minus y squared, and then dy, and then this is equal to -2, 3, y. If you simplify this, you get y squared plus 6y minus y cubed and dy. And then this will be 125 over 12. Okay, so that's the answer. And then now, it's okay to integrate with y first instead of x first, at least in principle. And then in that case, let me just mention this briefly. What if you fix x first and then integrate with y first. The answer is this. So we have this picture. Like this. And then this point is computed as 9, 3. And this point is computed as 4, negative 2. And then if you integrate with y first, namely you fix x first, depending on where you fix your x here, there are two different scenarios. So in this case, this is equal to, first of all, if you are on this part, and then for each fixed x, your y value varies from here to here, and that's gonna be negative root x to root x, y, and then you integrate with dy, and then you integrate with x, that's gonna be from 0 to 4, x value is 4, okay, this is 4, this point is 4. But on the other hand, if you fix your x, if you fix your x somewhere around here, and then your x is from the line to this upper part of the parabola, so this is plus x minus 6 y dy, and then upper part of the parabola, that's root x. And then you integrate with x, and that's from negative 4 to 9. Okay. And then in principle, you can just carry out this integral, but it's not a good idea. Not a good idea. Good idea. All right. But in principle, you could do this. All right, so that's pretty much the end of this video. And in the next video, I'll work out one more example, and then I'll briefly explain why this double integral actually gives you the volume, sort of like a proof for the double integral. Okay, that's what we're gonna do in the next video.